My name is Ben Schmidt. I'm the Chief Security Officer at Polyswarm, and today I'm going to be talking about smart contract honeypots. Assuming I can get to the next slide. There we go. So what this talk is going to cover are supposedly vulnerable contracts that aren't actually as vulnerable as they look when you look at them, that have actually been deployed in the wild. If you guys are participating in the Polyswarm Smart Contract Hacking Challenge, there's also some interesting tips in here that are related to this talk, so definitely pay attention. What this talk doesn't cover is how to find these honeypots. There's some active research that I'm doing on that, but it's not quite ready to publish yet. Scams that aren't about attacking attackers. So there's a ton of scams in the community, but they are not particularly technically interesting most of the time. And I'm definitely not going to be talking about the legal status of stealing money from people trying to hack things. I'm not a lawyer, but I would definitely not recommend doing anything in this presentation. So before we can start talking about these things, because a lot of these contracts are technically interesting, we need to understand how Ethereum works. So I'm going to give a quick crash course on both Ethereum and the major programming language, Solidity, so that you can understand how some of these contracts work internally. So funds in Ethereum are managed by account. It's just like a bank account, except your access is managed by a public-private key pair. Now there's two types of accounts: external accounts, which are these normal funded accounts that any normal person would use to send and receive funds. The other type is a special account called a contract account. Now these accounts actually manage the funds that are sent into them by executing code and determining how to distribute funds or not distribute funds based on this code deployed to the blockchain. Now accounts send and receive transactions, and what transactions are at their simplest form are proposed changes to the state of the Ethereum blockchain. So whenever you send something, as long as it doesn't violate consensus rules and you're paying enough money to get it included in a block, it will get included. Sorry, hope everyone has been able to hear me. So these transactions, to get them included, you have to pay fees to the miners to include them in a block. Now these fees are paid in Ether. These fees are important because they prevent people from spamming and filling up the blockchain, and they make everything that you do have an associated cost to it. So you need some small amount of money to get anything processed. You can think about it as a transaction fee. Once a transaction is confirmed, the state changes are immutable and stored forever, and more or less, it's now the truth of the blockchain that everyone can see. So all contracts, these contract accounts are executed on the EVM. So basically, you compile down some code normally. You don't normally write these assembly instructions yourself, but there's a series of instructions that get executed, and they will modify the chain in whatever way that you tell them to. So each one of these instructions has an associated gas cost, which means that if you do a lot of stuff, you might not be able to afford the changes that you're proposing, and it won't actually get confirmed. So Solidity is what most people write in. So they don't write this EVM bytecode. Solidity, it's by far the most widely used programming language that targets the EVM. It is statically typed, it's Turing complete, and it's sort of like JavaScript, but not. But it allows you to more easily manage the funds that go, how these funds are transferred between accounts in your contract. So this is a simple example. All it does is let you store a simple string to the chain and allows you to view it in a particular way. So each one of these contracts has a constructor, and it's a special function that sets the initial state of the chain to whatever you want it to be. So you supply some arguments, and it sets the initial state, and then from there, all these other functions that you call in the contract will update that state and potentially allow you to do interesting things to it. So functions in all contracts are, by default, public. So anyone on the network can call into this, and depending on what happens, it will confirm, or it'll get reverted, or something will happen. So each contract also has one unnamed function. Now this unnamed function is a fallback function. It determines what happens when you just send a transaction to a contract, but don't actually specify what function you want to execute, or if you specify a function that does not exist. So this is a last-ditch effort to make sure something happens whenever you send money to a contract. In most cases, it'll just fail if it's not intended, but some contracts actually accept funds when you don't actually call a function. So functions are called by sending a transaction with associated transaction data. Now this transaction data is pretty simple, and it's well defined. It consists of a method ID, which is a shortened hash of the name of the function and the arguments of the function. After you specify that hash, you also supply encoded arguments. So you'll put in a number, or you'll put in some string that you want to be stored or processed by the contract, and it'll be executed. Now, constructing data is handled transparently by Web3 bindings in most cases, but if you don't have contract source, it can be a little bit tricky to figure out what the original arguments were. So in addition to directly calling into contracts, contracts themselves are actually allowed to call functions in other contract accounts. So if you deploy a contract and it needs to access some other contract, so you want to log some data in a separate place, you can actually call into other contracts, and you get very complex chains of data at that point. So you can get one contract calls into contract A, calls into contract B, calls into contract C. All of these message calls, or internal transactions as Etherscan calls them, allow you to do things like implement libraries or implement much more modular code bases. However, it also makes things a lot more complicated at times when there's interactions between these contracts that you didn't expect. So this is an example of what it looks like in Etherscan whenever a contract calls into other contracts. And as you can see, there's a trace. So every single time this happens, an event is generated, and you could see that things are calling into each contract. This is actually an exploit attempt, but there are normal reasons why this would happen. So we've been talking a bit about how contracts store and update state. All contracts are able to store state between invocations in an area called storage. It's a key value store that maps 256-bit words to other 256-bit words. So what that essentially means is that starting at 0, you can write 256 bits at a time, and that's what the byte code that you're executing is actually updating whenever you're trying to update chain state. There's two other places where your contract code can store data, but it's not persistent. So it can use memory or stack. So they're much, much cheaper to use because writing to a blockchain is very expensive because there's very limited space. So most contracts will try and keep most of their temporary calculations in memory or on the stack, but write them into storage whenever they've determined what needs to be stored. So interestingly, Solidity actually defaults to using storage, which can cause a lot of performance problems and also lead to some weird behaviors that we'll see later. But you have to explicitly declare otherwise if you actually want to make your code more efficient. So it's also important to know some of the common pitfalls and vulnerabilities that have been encountered while writing Solidity. Solidity is still under active development, so it's easy to make some of these mistakes, unfortunately. So the first one is unhandled reentrant flow. Now, unhandled reentrant control flow is an issue where one contract, contract A, calls into contract B, which then calls back into contract A, and undesirable state changes haven't actually been committed in contract A yet, leading to behaviors that were actually unexpected. So the biggest example of this was the DAO hack, where tens of millions of dollars were lost, and it actually led to a hard fork of the network to try and recover some of those funds. But the basic problem here is that prior to actually updating the account balances during a withdrawal, the contract allowed you to call into an attacker-controlled contract. So an attacker deployed a malicious contract, then forced a withdrawal to take place. So when the DAO contract called into this attacker contract, the attacker called right back into the same withdrawal function, which allowed them to remove all the Ethereum from the contract rather than just the Ethereum that was allocated to their account. So another common issue is Delegate calling into vulnerable libraries. This was most famously demonstrated in the Parody hack, which was another gigantic compromise. And essentially what it allowed you to do was Delegate call into a vulnerable library. Now, Delegate call basically transparently transitions the execution environment from the contract you called into to a library contract, as if it was the same contract that you were executing. Now, what this allowed the attacker to do was actually, remarkably, call into an initialization function that was mistakenly included in the library. This allowed them to set themselves as the sole owner of the contract, even though they weren't an owner at all. And then they were able to simply just withdraw the funds. Even simpler than this problem, however, are unprotected critical functions. So, as I mentioned earlier, all contract functions in Solidity are by default public. Anyone can call them. So if you forget to protect certain functions, it can actually lead to compromise. So it's very, very common that people forget to mark something as only owner, which means only the person that marked themselves as the owner of the contract can call into it. So when that happens, it can actually cause loss of funds or cause someone to be able to steal funds. The most famous case of this is the Parody Freeze, which happened a little while after the original Parody hack. They fixed the Delegate call issue, but you could still call directly into the library, which was not initialized, so it didn't actually have an owner. And you could set yourself as an owner of the contract and then terminate the library. What this meant is that all contracts that were calling into this library contract would then fail, and you couldn't move any funds out. Today, there's still no way to move that out. There's been discussion about it, but it probably will not happen. And the final one that's relevant today is improper handling of secrets. So obviously, on a public blockchain, keeping secrets is very difficult. So there's one of the more popular contracts out there are gambling applications. So playing roulette or poker or any number of different things where you need some trusted source of randomness. Well, if you can predict what those secrets are, then you can cheat at the game. So people still have a lot of trouble doing this, and it's not a particularly easy problem. So there's a lot of tools that are being developed for Ethereum. The main one that we're going to look at today is Etherscan. Now, Etherscan is what's known as a block explorer. So it allows you to inspect the blocks and transactions that are being confirmed to the network. So if you're interested in what's happening on the network and you want some way to view the transactions in an easy to read manner, you'd probably be using Etherscan. Now, unfortunately, it doesn't display all the information that might be relevant and sometimes displays things in a misleading way, which we'll get into in a bit. These are a bunch of other really interesting tools, and I definitely recommend checking them out, but they're not too relevant for the talk today. So this is what Etherscan looks like. So as I said, it indexes blocks and displays them. It allows you to search for things. It allows you to view things. And actually, they have a beta feature for actually directly interacting with contracts, so calling functions, etc. So one of the other features that they have, and this is relevant to a lot of the honeypots we're going to look at today, is their verified code feature. Now, what Etherscan lets you do is actually upload the source code to a given contract, and it will compile it using the Solc compiler, which is what you use to compile Solidity contracts, and it will verify that the bytecode exactly matches the source code, the result of compiling the source code that you uploaded. So whenever you upload something that is valid, it gives it a nice, clean, green check mark, and it's presumed that this is the exact source code that led to the creation of this contract. So with that intro sort of out of the way, let's get into smart contracts. So why are these even a thing? Well, a lot of people think, a lot of attackers like to think that, irrevocable transfers plus bad code more or less equals free money. So there's a lot of people looking to find the next parody bug, the next DAO hack, and they want these tens of millions of dollars. So a lot of these people are pretty new to the ecosystem, however, and are still learning some of the ins and outs. In addition, because a lot of the tooling is is still in early stages, it can present misleading information to these people trying to exploit these things. Well, some enterprising hackers decided I could take advantage of this and deploy things that look vulnerable but are actually exploitative. So there are contracts that require people to send money into them to try and exploit a bug, but they actually can't exploit that bug and they lose their money. So I first got interested in these when I was running a challenge at Hack in the Box Amsterdam. So it's very similar to the challenge that we're running today. I deployed a vulnerable contract for this challenge, and it was called the HODL wallet. So the bug was a very classic reentrancy attack, similar to the DAO hack. The difference is that the account balance was actually updated prior to calling into the other contract. So you couldn't actually withdraw all the ether from the contract, but you could bypass the limits I had set on withdrawals from that account. So rather than only being able to withdraw a dollar worth of Ethereum, you could withdraw about $40 worth of Ethereum. And once you did that, we gave a bonus to people who were able to do it first. So interestingly, less than an hour before I deployed this and uploaded the source code to Etherscan for people to view, someone tried to deposit funds into the account and actually started trying to exploit the bug. This was very interesting because the contract was very explicitly designed to not allow you to interact with it and actually exploit the bug unless you were in a whitelist that I had provided. So the attacker had no chance of actually exploiting this, but actually got his funds stuck in the contract because he was unable to actually exploit it. Now, I hadn't set any minimum deposits on this contract, but if I had, it's possible that this person could have lost a significant amount of money. So I got interested in whether or not these things were common, and it actually turns out that there was a bit of an industry around this where people were coming up with new tricks to steal attackers' money. So my first example that wasn't so accidental is something called the private bank. So in February, a Reddit user posted about an interesting contract that he had found that he thought was vulnerable, and being the kind internet citizen that he is, attempted to exploit the contract and said he was going to give it back if it worked. So the contract, the private bank, was a very simple wallet contract. It had a very obvious reentrancy vulnerability, almost seemingly taken from Solidity warning documents telling you not to do this. But basically, it looked like you could call into your own contract and do it multiple times and withdraw the entire balance of the contract. So to be careful, the user actually tested their exploit on the testnet. The person who deployed this malicious honeypot had helpfully uploaded the source code to Etherscan so that people could see the bug more easily. And when this user went to go attempt to exploit it on the testnet from the source code that was provided, his exploit succeeded. However, whenever he went to deploy it, went to execute this exploit on the mainnet, it failed mysteriously. So it was very confusing why this would ever happen. So what's the problem here? And the problem is internal transactions. So in this contract, as a withdrawal is being made, it actually calls into a log function called transfer log. And they helpfully provided the source code to the log contract. And upon inspection, everything looks fine. It looks perfectly safe to execute this, and there's no reason it would cause a transaction to fail. However, in actuality, this function was the key to preventing people from actually exploiting the contract. So and this is because of how Etherscan actually verifies the contract source that you provide. So rather than compiling every single contract that is provided in a source file, because it actually only compiles one contract that you specify, and any calls into external contracts just make sure that the function signature matches. So or the method ID matches rather. So when you compile this source code, it doesn't actually compile the log contract. What it does is make sure that the ABI is correct. So when the attacker actually went to deploy this contract, they deployed a closed source contract, which was entirely different from the source code that they provided to Etherscan. This log contract would actually revert anyone's transaction unless it was theirs. So you could verify this by looking at the actual transfer log address, and you cannot verify it with the provided source. In fact, it looks like a lot of code has been added. So this also means, interestingly, that even if you tested it, given the source code provided, you think your exploit works, but it doesn't actually. So that's a more technical attempt to steal people's money, but there's a lot of simpler approaches that people have taken. So another one that took advantage of some errors in displaying in Etherscan was whale giveaway. Now, in this one, they deployed a contract and uploaded the source code again to Etherscan, which validated perfectly. When you looked at it, it looked like as long as you sent 1 Ether into it, it would transfer the entire balance of the contract back to you. In actuality, however, hidden off thousands of spaces to the side was a check that only allowed that function to be called by the owner. So basically, it would send the entire balance of the contract to the person who deployed it rather than sending it to you. So an even simpler one, which I kind of think was brilliant in its approach, was that a user started going around into various chat rooms asking for help. And when he asked for help, he would post a private key instead of a public key. What was in the account were some shitcoins, for lack of a better word. The Ethereum coin is a random ERC20 token, and it appeared to have, at the time, thousands of dollars of this token in this account. So in theory, someone could take that private key and then transfer those out, and they'd have free money. What the account didn't have, though, was Ether. Now, if you remember, you have to actually pay for transactions on the network. So to send those tokens out from that account, you actually had to deposit Ethereum into it. So it wasn't actually that easy, however. What these attackers didn't know was that there was a script that was watching all the transactions to this account, and immediately after the fund transfer is confirmed, they'd just take the money out. In addition, the particular token that they had chosen has a quirk in its ERC20 contract. Now, all the tokens on the Ethereum network generally follow ERC20, which is a standard contract ABI for interacting with these with these tokens. One of the functions that they have is called balance of. So that's supposed to tell you how many tokens this particular address owns. Now, this contract also had an additional field called the available balance of. So what this ERC20 token allowed you to do was actually lock tokens so that you couldn't transfer them. So while it looked like there were thousands of dollars of tokens that were actually transferable, they actually weren't. So people kept trying to send money into this account and steal the tokens, and it wasn't even possible to take them in the first place. So this one is actually probably the most technically interesting to me, but it was a game called Crypto Roulette. So Crypto Roulette is a simple gambling smart contract. So if you guess the right number, you win some Ethereum. So this contract had a pretty obviously bad secret generation method, but even worse, it was storing the secret in a quote-unquote private variable. Now, in Solidity, when variables are private, that doesn't mean that nobody can read them. It just means that it isn't actually easily exposed to the user. So you could because you can directly read storage locations, you can directly read these private variables off the chain. It's a common mistake that people make, but it makes it very easy to compromise gambling apps because the secret is obvious to anyone who has access to the Ethereum network. So you guess the number that's stored on the chain, and you get some free ETH, right? Well, not quite. So the play function requires that you send a small amount of Ethereum in, the minimum bet, and if you're successful, it sends you the entire balance of the contract. Well, it may not be obvious from the source here, and that's intentional, but the number is actually not what you're reading off of the contract. So in this case, the attacker had actually declared an uninitialized pointer to a game structure. Now, looking at it, you would think that this person's just allocating a new quote-unquote game structure, initializing it with the values that they want, and storing the result. Unfortunately, what it's actually doing is writing to the 0th storage slot. So because it's uninitialized, its value is actually pointing to the first storage slot in storage. So whenever the user goes to call this function, message.sender gets written into player. What that's actually writing to is the secret number, quote unquote, on the chain. Because the number has to be less than 16, and it's exceedingly unlikely that your public address is less than 16, it's actually impossible to win this contest. So once a few people transferred funds in and failed to exploit it, the attacker went and collected all the funds. So the Multiplicator X3 contract was another pretty simple one. I'm not sure if this one is very obvious either, but the issue is that message.balance, message.value has to be greater than or equal to this .balance. So what someone reading this thinks is that if they send in more money than what is already in the contract, they're actually going to be able to transfer out the entirety of the balances. Well, the problem with this is that that is an impossible condition. Whenever you transfer funds into an account, this .balance is immediately updated. So whenever someone tries to send more money into this .balance is always going to be greater than message.value, causing them to lose all their funds. So these are some of the more interesting ones. There's a lot more out there. It's pretty undeniable that it's interesting to watch these attackers attack people who are trying to scam and hack and steal money. But they definitely demonstrate some serious issues with the common tools for viewing smart contracts, interacting with smart contracts, and validating that what a contract does is actually what you think it does. So there's a lot more work that needs to be done to make Solidity a little more intuitive and explicit as to what it's actually going to be doing. There's a lot more work that needs to be done on making viewers more of transactions and the blockchain in general to make it obvious what's actually occurring, rather than sort of misleading people as to what a given contract actually does. So hopefully we can work on some of those things moving forward, and some of these issues have already been addressed by Etherscan. Unfortunately, some of the issues with validating and verifying contracts haven't quite, but it's future work, and hopefully we can make things better. So that's all I have for right now. Do we have any questions? Okay. Well, thank you very much for your time.